Chemical bonds, whether they are ionic bonds or covalent bonds, happen because of the interactions between valence electrons for the different elements on the periodic table. Now, here we have a periodic table, and there is a group of elements on this table that we're going to pay more attention to than another group of elements. And so if you look here, okay, this is group 1, 2, this is a 13 that you can see on your table. It's a little difficult to see on the one I have here. 14, 15, 16, 17, and group 18. Okay, so these 8 groups make up what we call our representative elements. All right, we're going to skip groups 3 through 12 for right now. And there is something that we can do to help us visualize the bonds that are formed from these representative elements, and that is creating our electron dot diagrams. Okay, so we've looked at our representative elements, and I'm just going to put this on the paper, and everything that I'm putting on my document, you should be putting on your document. So the first thing that I'm going to do, I'm just going to write which groups on the periodic table represent the representative elements. All right, so once again, your representative elements are going to be, for you guys, groups 1, 2, 13 through 18. All right. Now, what is so special about these representative elements? Well, we also use Roman numerals to represent these groups. So it would be from Roman numeral 1 to Roman numeral 8. Okay. All right. And so the Roman numerals that represent these groups tell us the number of valence electrons they have. All right, so the electron dot diagrams that we're going to draw out are also the number of valence electrons. So see here, represents the number of valence electrons. Now, if I haven't told you this before, let me go ahead and tell you this now, and I'm going to write it down here. These are the valence electrons, are the electrons in the outer shell. All right, these are the ones that they use to form the different bonds that we've looked at. All right, I just want to give you a couple of rules when it comes to electron dot diagrams. You're gonna, first rule is that there is a maximum of 2 electrons, and I'm going to represent electrons with the E negative. Okay, 2 electrons on each side. So think about your symbols for your elements being in a box. Okay, and so there will be 4 sides, and you'll have a maximum of 2 electrons on each side. So this is going to give you a maximum of 8 electrons, okay, around the symbol. And this makes sense because if you look at how high the Roman numeral goes, it only goes up to 8. All right, so we're not dealing with more than 8 valence electrons. And then there's one more rule, and that is you will put 1 electron on each side before you double up. Okay, so it'll be 1 electron on each side before you double up. Oh, and I guess I should put this as a rule or just as a thing. that your electrons are represented by dots. Okay, hence electron dot diagram. All right, and so what we're going to do is we're going to pick elements from these 8 groups that are our representative elements. And so what I'm going to do is I'm going to use period 3, which starts with sodium and goes all the way to argon. Okay, and those are going to be my 8 elements that I'm using. Okay, so I'm going to go ahead and put the symbols kind of in the middle. So sodium's Na, magnesium's Mg, aluminum's Al, then we have silicon, which is Si, phosphorus, sulfur, chlorine, and we're ending with argon. All right, so once again, if we look at these in terms of the Roman numerals, so this is Roman numeral 1, 2, 3, 4, 5, 6, 7, 8. Those are the number of electrons, and they will represent the number of dots that we have. So sodium is in group 1, so it will have 1 dot. And so let me represent that. I start my right on the right here, and then I go counterclockwise with the dots, and so you'll see that here. So here's my 1 dot for the sodium. Magnesium and the other elements that are in group 2 will have 2 dots because they have 2 valence electrons. Aluminum and the other elements in group 3, 3 valence electrons, and we represent that by 3 dots. Silicon and its other family members, 4 valence electrons, and we have 4 dots to represent those 4 valence electrons. Phosphorus, group 5, 5 valence electrons, and so we'll have 5 dots to represent those 5 valence electrons. Sulfur, group 6, 6 valence electrons, so we'll represent that with the 6 dots. So let's get those dots in. All right, chlorine and its family members, 7 valence electrons, and so we'll have 7 dots here. Trying to close them here. And then argon is in group 8 with 8 valence electrons, and so we'll have 8 dots around argon. And what you want to do, because you're thinking about this as being a symbol in a box, and so you have your dots on each side, you want them to look like they're paired up as well. So you don't want to space them out so far that it just, doesn't look like they're on a side. Okay. There is one exception to what we just went through here, and that is with our group 8. The first element is helium. Helium only has 2 electrons, and so helium, I'm going to put it off to the side. Okay, helium with its 2 electrons, period. It only has 1 energy level, and that level is full with the 2 electrons. All right, so helium does not have 8 dots around it representing 8 valence electrons. All right, and so there's just a little bit of information I want to give you regarding these elements, these representative elements. And so if you look here, groups 1, 2, 3 represent metals. All right, metals lose electrons when they're forming ionic bonds. All right, groups 5, 6, and 7 are nonmetals. Nonmetals tend to gain electrons when they form ionic bonds. So metals lose, nonmetals gain. All right, and so losing electrons, you have more positive particles and negative particles, so they have an overall positive charge. Gaining electrons, you have more negative particles than positive, so the overall charge would be negative. Group 4, you really have all three types of elements in group 4. You have nonmetals, metalloids, and metals in this group, but they have 4 valence electrons, and they it depends on the bond that is formed. They could lose, okay, 4 electrons or 2, and they can gain those electrons. And then you have group 8. They have what we call a full octet. So they have their 8 valence electrons, and unless it is under special conditions, they are not going to react with other substances. So they're not losing or gaining. And then, of course, we know with our nonmetals, they also participate in covalent bonds where they share electrons. But right now, let's just look at ionic. All right, so group 1, this group, they lose, the group loses 1 electron to form a 1 positive or just positive cation. And a cation is a positive ion, just in case you didn't know that. And then in group 2, what they're going to do, they lose 2 electrons, and they form a 2 positive cation. And then, of course, in this group here, we'll lose 3 electrons to form a 3 positive cation. All right, and then I wanted to skip down to the negative group that I was telling you guys about. All right, so this group is that, can you see that? No, I just continue to write in black. Okay, gains 3 electrons forms a 3 negative anion. And this group here gains 2 electrons to form a 2 negative anion. All right, this group here gains 1 electron to form a 1 negative anion. All right, and then I wanted to just look back at our positive and negative ions, our cations and our anions. Okay, they form chemical bonds to achieve a stable, all right, a stable outer shell. And normally to have a stable outer shell, you need 8 valence electrons. And so our metals are going to lose these. So metals lose electrons to form a stable octet. So when they lose this 1, 2, or 3 electrons, the electrons that are in the level above it, you have 8 of them, and they're considered stable. Whereas your nonmetals, on the flip side, they are gaining electrons to form their stable octet. All right, and so when you know how many valence electrons they have, and you know the goal is to get to 8, well, you look here. If you have 5 and you want 8, you just need to get 3 more. You have 6, you want 8, you need to get 2 more. You have 7, you want 8, you need to get 1 more. All right, and it's also an energy ploy here. It takes less energy for them to gain than to lose. It takes less energy for this group to lose versus to gain. All right, so let's look at our other 2 groups that I have not completed. What happens here, like I said, with this group right here, it's like they go either way. So this group, they can lose or gain 4 electrons. So it's either going to be, if it's losing, they'll have a cation with a charge of 4 plus. If they gain, they'll have an anion with a charge of 4 negative, okay? And then this group here, they have the 8 valence electrons. And normally, like I said, normally they are not losing or gaining electrons. Okay, so this group has the octet, and I'm just going to write that down for you guys so you'll know how to spell it. Okay, octet, O-C-T-E-T, 8 valence electrons. And I don't want to forget about helium over here. Helium will never achieve an octet because it will not get 8 valence electrons, but it will achieve something called a duet, which would be 2 valence electrons. Okay? All right, and here's the wonderful thing about this electron dot diagram handout that you have here, and it is now completed for you guys. This applies to all of the elements that are in this group. So it doesn't matter if I give you lithium, if I give you potassium, if I give you rubidium, whatever I give you, if it falls under group 1, it has 1 valence electron, and when it forms an ionic bond, it's going to lose that valence electron, okay, to form a 1 plus cation. Same thing with group 7. If I give you fluorine, if I give you iodine, it doesn't matter what I give you. If it's from group 7, it already has 7 valence electrons, and when it's forming an ionic bond, it is going to gain 1 more electron to become a 1 negative anion. All right. If you have any further questions, just let me know.